Um, so before we start the physics panel, I just wanted to welcome everyone to day 2. Can everyone hear me? Yeah. Thank you to everyone who joined yesterday. We had an awesome time learning about microbes and nanotechnology, neurobiology, probabilistic combinatorics, and many other amazing STEM concepts. And today we're going to be diving into physics, computer science, and engineering. And so at the end of the day, we're also going to have multiple undergraduate students talk about their extracurriculars in STEM and opportunities that encourage them to pursue STEM and help them rise to the challenge of attending some of the top U.S. universities. So we're now going to kick off with the physics panel, where we're going to get to peer into the proton, discover black holes colliding at the edge of the universe, quantum computers, and dive into the mysteries of the physical universe. So joining us bright and early is Dr. Richard Conhenry, an Academy Professor of Physics and Astronomy at Johns Hopkins University. Dr. Henry has made observations using the Copernicus and IUE satellites, as well as the Hubble Space Telescope and the Mariner 9 spacecraft, and was a co-investigator on Apollo 17 and the Apollo Soyuz mission. He's the principal investigator in the study of the lunar material, and he's also the PI for the Hopkins Ultraviolet Background Explorer, which was selected in 1996 April as a NASA MidX program alternate project. So without further ado, please welcome Dr. Henry.
Howdy. You've heard it claimed that a picture is worth 1,000 words. But to our astonishment, we humans have discovered that an equation is worth 1,000 pictures. Hey, at least 1,000. How can that be? An equation? Surely you jest. Hi, I'm Dick Henry, and I'm director of NASA's Maryland Space Grant Consortium, and I'm also an Academy Professor at the Johns Hopkins University in Baltimore, Maryland. My PhD is in astronomy, but I've also taught physics for decades, endlessly trying to understand that mysterious subject. When I finally did understand, well, at least I think I understand, I wrote it up as an essay and I submitted it to the famous international journal Nature. And by gum, it was published. The Mental Universe. Just Google it. You see, while I'd always found mathematics easy and interesting, physics was, to me, incomprehensible. It didn't seem to fit the world I actually lived in. Equations, boo. But then I was incredibly lucky. I was hired as an assistant professor in a physics department. Hey, they hired me because they needed an astronomer, but that gave me the chance to teach physics, and with wonderful results. It did take a long time, decades, but I got there. So what is the result? I can share it with you all very easily indeed, because it turns out to be simple after you've gotten there. The universe is intrinsically mathematical in its very bones. If you understand math, which is easy, you can understand the universe. So exactly where do we start? You start with the Pythagorean theorem, which is the most important single result in all of mathematics, and as it turned out, the most important single result in all of physics as well. You all know the theorem. Heck, everybody knows the theorem. The square on the hypotenuse is equal to the sum of the squares on the other two sides. Even the straw man knew a, well, somewhat garbled version of that. So why is the Pythagorean theorem so important? It is because that theorem miraculously turned out to be the gateway to our understanding the nature of time. Time, which is by far the most mysterious feature of our universe and of our own existence. Well, who was it that discovered that about the ancient Pythagorean theorem? No, It wasn't Albert Einstein. It was one of Albert Einstein's former teachers in Switzerland, Hermann Minkowski. Yes, it is true, precocious young Einstein had in 1905 discovered his special relativity. Wow, indeed. But just 3 years later, it was Hermann Minkowski, a former teacher of Einstein, who discovered just what special relativity really meant. Relativity, Minkowski discovered, is nothing but a mathematically trivial extension of the famous Pythagorean theorem to include time as a fourth dimension. I consider that to be the biggest human discovery ever. You can write the 3D Pythagorean theorem as an algebraic equation, the sum of three squared terms. Why three? Three because space has three dimensions. You would add one more term, wouldn't you, if it had turned out that space had four dimensions? Of course you would. And parking would have been much easier. But space doesn't have fourth dimensions. It has only three. Well, here's the enormous yet trivial secret. Instead of adding one more term, you use, for time, that fourth term, a minus sign instead of a plus sign. That's it, the greatest discovery in the history of physics. Well, that's the end of the story. The most important discovery about the nature of the universe ever made, mathematically trivial, yet incredibly consequential for physics, for engineering, for philosophy, perhaps even for religion. The nature of time. Simply a minus sign in the Pythagorean theorem. So, what great difference did Einstein and Minkowski's discovery make? For one thing, it is what allowed us to actually understand, at long last, what underlies the incredibly important earlier physics discoveries that had been made by Sir Isaac Newton. Just think what Newton had accomplished. He and his followers had discovered wonderful things. Yes, but all of them were things that they could not actually understand at all. Conservation of energy, conservation of momentum, conservation of angular momentum, and Newton's famous law of gravitation. Yes, but where did these wonders come from? Why were they true? Experimental test plus extremely detailed observations showed all these to be true, but no one knew why they were true. Indeed, Newton was deeply embarrassed by his inability to explain the wonders that he had uncovered. Well, Hermann Minkowski's brilliant reinterpretation of Einstein's new special relativity as being nothing but an extension of the Pythagorean theorem to include time as an additional dimension, but with a minus sign, not a plus sign, allowed immediate rewriting of all of physics to include time finally in its actual and proper role. Nothing hard about it, just a great long bunch of mathematics. You don't even need to go through it all. You can just use the wonderful results. Hold it. Just a bunch of mathematics, algebra? Let's pause and think a bit about that. How can the universe possibly understand our mathematics, our algebra, much less use it, when algebra didn't even exist until we humans thought it up? And wait a minute, how the heck could naked apes like us think up algebra? Well, let's take a serious pause now and go back and review all of ancient human history. The naked apes, our ancestors, had been around for a long, long time. But until about 50,000 years ago, we Homo sapiens did not, could not talk. But at that point, the FOXP2 gene appeared just in a small group of about 50,000 of us in East Africa. We were not the only people on Earth. There were a couple of million people, but every single person on Earth today is descended just from those particular 50,000 people and not from all those others, simply because our ancestors were the people that acquired speech. A click language. There are still today in Africa peoples who speak click languages, including a language that may be the original click language. Oh, just imagine that you were that child, the first child to say, pick up a stone and think to say, while pointing to the stone. Another child mimics you. It's a fun game. Another child picks up a stick and says, the game continues day after day. And the first human language has appeared. Among the kids is, my bet, a turning point in human destiny. Not all the kids were able to keep up, but those that did became fluent, had hugely successful hunting parties because they could plan and coordinate and communicate. Within some generations, that whole tribe of humans had become talkers. Hey, we've never stopped talking since. I'm doing it right now. Fast forward to ancient Greece. All Greeks talked, obviously, but a few had also developed something totally new: geometry, diagrams, brilliant geometry over some hundreds of years. But none of them thought up what we now call algebra to represent that geometry with abstract and arbitrary symbols. Even so, one brilliant Greek, Pythagoras, in addition to creating his famous theorem, recognized that, quote, number is all things, which is what we finally are realizing today. For Pythagoras seemed to know that hiding within the wonderful geometry lurk numbers, algebra. Once finally discovered, and it did take a long, long time, meant that you could write the Pythagorean theorem without drawing any triangles. Algebra was essential in allowing that extension to the Pythagorean theorem that we today call Einstein's theory of relativity, because only very clumsy diagrams could sort of include time, and really only in a fake manner. But algebra includes time easily, without missing a beat. Just that simple minus sign. For there are no minus signs in diagrams. There can be in equations. It's as simple as that. Victory. But wait, there's more. Recall that Newton and his followers did find conservation laws. Energy, momentum, angular momentum. Yes, but no one had any idea why these laws held true. Do any of you know who it was that made the crucial discovery as to why these laws are true? You don't know? Then one guess as to the gender of the person who made this second most fundamental discovery ever in the history of physics. The person who found out why was an American mathematician named Emmy Noether. After Pythagoras himself, she is the greatest contributor to our understanding of the nature of the universe. For Emmy discovered why there are conservation laws. And it is utterly simple. Each conservation law exists only because there is a particular symmetry present for unknown reasons in our universe. And all it takes is simple algebra to show that what Emmy discovered is true, that is why conservation laws exist and must exist. Here is her result in words. 1. If you do an experiment of any kind and you repeat it later, you get the same result, and that is why energy is concerned. 2. If you do an experiment of any kind and you also do it across the room, you get the same result there, and that is why linear momentum is conserved. 3. If you repeat an experiment about rotating it some, you get the same result rotated, and that is why angular momentum is conserved. Well, wow, we now know why. Even today, we don't know why the universe has those symmetries, except that if it did not, we ourselves could not exist. Now, to make it even better, suppose you try one more thing. Instead of weighting or shifting or rotating your experiment, you create a mirror image version of your experiment. Well, I guess you expect that you'll get the same result, but mirror imaged. Hey, let's give that hypothesis a name. We'll label it. Oh, we do love obscure terminology, conservation of parity. If it turns out by experiment to be true, like the other ones did turn out by experiment to be true. And yes, indeed, for experiments that involve the gravitational force or the nuclear force or the electromagnetic force, yep, same old, conservation this time of parity as it is called in the jargon. It is just a word, but it is a real symmetry by experiment. But if your experiment involves the fourth of the four forces, the so-called weak interaction, for example, as seen in neutron decay, you get a different result. Non-conservation of parity, Nobel Prizes. Wow, our universe has a very peculiar structure embedded in its mathematical bones. There are no right-handed neutrinos. This is a fact. Now, let's go back to Einstein and Minkowski's great discovery of the geometrical nature of time, that minus sign. Well, Albert Einstein, bless the poor fellow, for about 1 year, he resisted his teacher, Hermann Minkowski's reinterpretation of Einstein's already famous relativity as being merely a trivial extension of the Pythagorean theorem. But fortunately, good old Albert did see the light. And indeed, he saw it so clearly that it was what led in 1917 directly to Einstein's greatest accomplishment, his experimentally verified theory of gravitation, called, for some reason, general relativity. Now, remember how embarrassed Newton was about his hugely successful theory of gravitation? He couldn't explain why it worked. Well, a light bulb had gone off in Albert Einstein's head. Maybe space-time is not flat, but is curved. You've heard that before. Then, if a great mass, such as our sun, was somehow, we still don't know why, the cause of that curvature, the planets would naturally follow curved paths, orbits. Okay, sounds like an idea at least worth trying. Just a bunch of math to work it all out. And hey, the heavy lifting had already been done by the pure mathematicians, Gauss and Riemann. Well, by gum, just a few years of effort by Albert during World War I, and bingo, Einstein's crowning achievement, his famous theory of general relativity. The equations are extremely simple. Here it is in words. Curvature equals mass energy. Uh-oh, wait a minute. Take a look at that, careful. Mass energy is conserved, but curvature, it turns out, is not. That is, its derivative with time is not zero. Shucks. But Einstein persisted. He said, okay, let me tweak curvature to get something that is conserved. Well, would you have bet on that? I wouldn't. I'd have given up. But by gum, it worked. Wonderful. And that's where the story gets incredibly exciting. For World War I was on. Einstein auf Deutschland published his equations. Equations that he, Einstein, never could solve other than numerically, which Einstein had done to verify that they worked by showing that they explained perfectly the mysterious observed precession of the perihelion of the planet Mercury, the only deviation that had ever been discovered from Newton's problematic law of gravitation. Well, apart from what led to the discovery of Neptune by Leverrier. Well, then, wait for it, a miracle happened. On the German World War I Eastern Front, physicist soldier Karl Schwarzschild received his copy of the journal in which Einstein's general relativity was published, and Karl solved the equations, and they predicted black holes. The rest is history. And guess what? You'll never guess. Schwarzschild's solution that predicted black holes was a slight modification of the Pythagorean theorem. Oh my God, I'll stop there. I can't take it anymore. It's too exciting for me. Oh, wait. I've just realized that I have not yet mentioned quantum mechanics. And that might seem to you to be derelict of me. So let me deal with quantum mechanics, which most unfortunately is what almost everyone thinks is the most mysterious thing in all of physics. Oh yes, I myself certainly did feel that exact same way at one time. But fortunately, it dawned on me that surely quantum mechanics must be the result of the same symmetries that produced the conservation laws. And so it turned out. I spent a summer at Los Alamos National Laboratory, starting from scratch to see if I could produce quantum mechanics from nothing. And I succeeded. Quantum mechanics made transparent, published after thorough peer review in the American Journal of Physics. Hey, no joke, 4 referees, all 4 supported. Well, that was long ago, 1990. That paper has only been referenced in more recent papers one single time. But that one reference was by, brace yourself, Isaac Newton, no less. Now you may think that that is impossible, but I assure you that it is true, for I should know. I was Isaac's co-author. And I am very happy indeed to be able to report that there is a later paper by a different author establishing exactly the same thing, namely that quantum mechanics is just a simple product of the mysterious presence of symmetries in the universe. That paper is by the late Moshe Shapiro, and I give a reference. Wow. At that point, I, of course, entirely lost all interest in quantum mechanics. I had turned quantum mechanics into a dull subject. And I must say, to me, It is bizarre that so many people, even physicists, still think that quantum mechanics is mysterious. Well, that's physics. Now for the big question, what does it all mean? My answer, sorry, I haven't any really defensible idea as to what it does all mean. However, I do assert that I do know for sure what it does not mean. Experiment has shown that there is no universe out there in the conventional sense. Bishop Berkeley was correct. There's nothing out there despite all our observations. Yes, of course, we make observations. You're making them now. But they are not observations of anything, as in anything. By experiment, we know that there are no things. What there are observations, and those observations are, of course, in our minds. They are purely mental, looked at closely, and we have looked at them closely, extremely closely. There is nothing there, as in no thing there. There are no things. There are only observations. I like to call them records. The universe is clearly and most definitely not material, since there is no material. So they must be mental, because my mind, and you will agree, your mind, do vividly perceive them. What are we to make of that? What I make of it is that you and I are incredibly, indeed almost inconceivably, fortunate to exist, to experience the magic of life. I am so grateful. Whatever the universe actually is, in actual practice, the astronomer's universe out there is utterly hostile to life of any kind. Our planet Earth is a lifeboat in an ocean of destructive high-energy radiation. Particles accelerated from our sun, also particles accelerated by the magnetic fields in the galaxy of stars where our sun enjoys its existence. So do take care of planet Earth and do learn physics, the key to understanding the beautiful world that you are enjoying this very day. Oh yes, my own research. I have published dozens of investigations of the cosmic diffuse ultraviolet background radiation from our universe. My interest in it today centers on the possibility that a component of it originates in the very slow decay of the dark matter particles with the emission of ultraviolet photons that are capable of ionizing hydrogen. The idea is that that is how the universe managed to achieve its present extremely high degree of ionization, following the universe's recombination just 380,000 years after the Big Bang. Next up on this, I hope to make observations using an instrument that is on board the New Horizons mission, which is now well beyond Pluto. We'll see. So, any questions from anyone?
I have okay. I have a rather abstract question, but what was it like working with like the Hubble Space Telescope and like all the Copernicus and IUE satellites? Like what's your favorite part about it? And yeah.
The Hubble Space Telescope, oh my goodness, my goodness. I was a graduate student at Princeton. Lyman Spitzer there was the inventor of the concept of space telescope. And when I was at Johns Hopkins University and I was invited to go down to NASA headquarters for 2 years to be deputy director of the astrophysics division, we managed to get Jimmy Carter to fund the Hubble Space Telescope. And then I went back to Johns Hopkins, and extraordinarily enough, instead of the Hubble Space Telescope going to Princeton, which everybody thought it would, it ended up on my own campus. I had nothing to do with it. I had tremendous colleagues. And I've observed with the Hubble long ago. It's wonderful having it still up there working.
That sounds awesome. Also, if you're watching from the live stream, I know there's like a little bit of a lag, but oh yes, okay. Someone actually asked something on a live stream. They asked, what do you do on a day-to-day basis?
Oh, on a day-to-day basis, I stay in this house. And on a day-to-day basis, I work away on plans for using the New Horizons mission. They've got an ultraviolet spectrometer on board, which if I can convince the system to allow me to use it for my observations, should be able to analyze that diffuse ultraviolet background. And most people, the overwhelming majority of astronomers, believe that the ultraviolet background is simply backscattered light from hot stars in our own galaxy. And I'm convinced, for whatever reason, that that is not the case, that a good fraction of it is in fact a dark matter decay. And the nature of the dark matter is the most outstanding, huge problem in physics today. Nobody knows what it is. But I'm not the only person who thinks he or she knows what it is. There's dozens of us around the world, and we all have different ideas, and we all think the others are wrong and we're right. And that's what makes physics and astronomy so exciting. And in the end, hopefully we really will find out what the mysterious dark matter actually is. As I say, I think it's a light particle. I think it decays with a very long lifetime, and with the emission of 2 photons, it would have to be 2 photons because the dark matter is not electrically charged, we know that. And those photons are what cause the reionization of the universe. Almost all the hydrogen in the universe is ionized, almost all of it, 99.9%. And nobody really knows what caused that ionization. It's simply extraordinary. That problem has to be solved. And the dark matter would be a twofer. So I just hope I get to do that.
How can you get into like physics and astronomy from
I'm sorry, the sound that's coming through here is very unclear to me. Clearer?
How could you get into physics or astronomy from an earlier age?
That's a good question. I suspect what happened, we used to go up to Georgian Bay, and one morning I woke up and my parents said, "Oh, Richard, there was the most wonderful display of northern lights. Wonderful." And I said, "Why didn't you wake me up?" And they said, "Oh, we thought you needed your sleep." I think that's what turned me into a scientist. I've really been an astronomer since I was a kid. I have a telescope. Oh boy.
Did you see the comet?
No, I did not see the current comet. At my age, I just turned 80, and I am in perfectly good health, but I don't go out and look at the sky anymore. Did you see the comet?
Yes.
Yeah. Was it good?
Yeah, it was pretty cool. It was bright.
I love the fact that comets have 2 tails. I mean, that's absolutely marvelous. The ion tail that points directly away from the sun, and then the dust tail that is influenced by the solar wind. That's how the solar wind was discovered. It's really wonderful stuff. I was also on Apollo 17. Oh, I had so much fun on Apollo 17. Believe it or not, my senior colleague and I had a ultraviolet spectrometer on board the lunar orbiting mission part of it. And on the way back from the moon, we got invited into the famous control room for Chinese food on the last sleep cycle while the astronauts were sleeping on the way back from the moon. And I knew that they were sleeping and the thing was rotating, and I was the one who decided what angle it would be rotating at, because the spectrometer was observing my targets on the Apollo 17 mission. I've had an exciting life. I told you, I think in the blurb, that I'd hitchhiked across the Sahara Desert and went down the Nile on a barge. Wow, have fun while you can. I'm having fun right now. And I thank you so much for inviting me to talk.
Thank you so much, Dr. Henry. We do have a few more questions for you, but we do have to move on because it's 8:35. Do you think you could, I could send them to you later, or just you could answer them?
I
Oh,
don't
okay.
think, I don't think I'll be able to
Dr.
be
Gleiser just said.
available later, unfortunately.
Okay, no,
I'll turn my
that's totally
sound
fine.
off now.
Sorry?
Shall I turn my sound off now? I guess I should. Mute.
Oh yeah, thank you so
Bye,
much.
thank you again.
Well, first, thank you so much, Dr. Henry. Okay, your questions will be answered, Perry Ivan and Jay Kennedy, but by Dr. Gleiser. Okay, bye, Dr. Henry. Thank you so much.